In this session we discuss Carnot Engine, the basic of or the heat engine. Carnot Engine was the man who proposed the working design of a heat engine. The heat energy is getting converted into mechanical energy. Nowadays we are depending on this Carnot Engine's engine type, that is petrol engine, diesel engine, steam engine, everything is the different modification of what we call the basic form of Carnot engine. Okay. So how to convert heat energy into mechanical work? So Carnot engine is having three main parts, that are: one, source of heat. Source of heat. This is also called hot reservoir. Okay. So source of heat is actually the system where heat energy is providing for the working of the engine. So provider of heat. So if you take petrol engine, petrol is actually the fuel that supplies the heat energy required. Burning that petrol, we get the heat energy. Okay. So source of heat is where we can depend on what you call the heat energy required for the working of the engine. And theoretically speaking, this source of heat is always at a high temperature state that is having enough and more heat energy with it, so that you can take any amount of heat energy from the source that its energy is not decreasing. Theoretical condition. You can take any amount of heat energy from the heat source that its energy is not going to change. Second one is actually the working substance. Working substance. Working substance part. But actually, this working substance is absorbing heat from the source and convert that heat energy into work. That's why it's called working substance. It is actually a cylinder which is filled with gas, you can assume like that. A cylinder filled with a gas and is fitted with a movable piston. So that when the gas absorbs heat from the source, it expands, and it can be compressed also. By expansion and compression, the moving up and down of the piston, you can associate with what? The working. Okay? And the third one is that the heat sink. Heat sink is a very important portion of a heat engine. Heat sink is actually called the reservoir that it can absorb any amount of heat so that its temperature is not increasing. It is such a low energy state that it can absorb any amount of heat so its temperature is not increasing. Now why this heat sink is required? Because after doing work, the working substance is left with some amount of heat energy inside. That heat energy must be removed from that working substance. For that we use heat sink. Actually, heat sink is a heat remover. Understood? So these three are the three main parts of what we call a Carnot engine. Now this working substance absorbs heat from the source. So heat energy is absorbed from the source. And this piston, say as the gas expands, piston moves up. So there is a work is being done. So this piston movement up and down will be associated with the rotating wheel, so that as the piston moves up, the wheel rotates to half, and the next half the wheel continue to rotate, that the piston will be coming down, compression also takes place. So like that, up and down motion continues. So here at this stage, we will be getting the work output. Work output. Then, after doing the work, some amount of heat energy is left with the working substance that is given to the sink. So, working substance is kept in contact with the sink so that the heat energy remaining will be absorbed by the sink. So that the working substance is now under ordinary condition now. That it can absorb heat from the source again. Thus what remain can be given. So like that the process will be continuing. So expansion and compression of the gas is coming, still the piston will be moving up and down. This up and down motion can be coupled with a rotating wheel. As the wheel rotates, that rotation can be taken out, so move what you call a locomotive or something like that. This is actually the working of what you call a Carnot engine, the very basic part of it. Okay? Now, we want to discuss the efficiency of the Carnot engine. Efficiency. What is efficiency means? How efficient this engine is. It can be calculated by the equation as the ratio of output by input. Output energy divided by input energy. So here we are inputting the energy in the form of heat and we are getting the output in the form of work. So efficiency can be equal to work output divided by heat input. This is actually the efficiency. Okay. So to understand that, let us say an amount of energy Q1 is absorbed by the substance and it does work, and let Q2 be the heat energy given to the sink by the working substance. Then Q1 minus Q2 will be the amount of heat energy that may get converted into work. Okay? Because Q1 is the energy absorbed from the source and Q2 is the energy given to the sink, then Q1 minus Q2 will be the amount of work we can expect. Therefore, efficiency eta can be equal to work output, that is Q1 minus Q2 divided by heat input Q1, or it is equal to 1 minus Q2 by Q1. Okay? So you will be expressing this in percentage by multiplying right hand side with 100 so that you can express efficiency in percentage. Efficiency is always expressed in percentage. Okay? Now the same equation you can have it in terms of temperature, because heat energy is directly proportional to the temperature of the system. Therefore, if I take the gas energy in terms of temperature, we know that Q1 is proportional to T1, absolute state, and Q2 will be directly proportional to T2. Therefore, the efficiency eta can again be written as T1 minus T2 by T1, or eta equal to 1 minus T2 by T1. Remember, T1 greater than T2, and here Q1 greater than Q2. Because Q1 and T1 are the source condition, it's a hot reservoir condition, and Q2 and T2 are the cold reservoir condition, it's less varieties. And using this equation you can find the efficiency of the heat engine, and remember, no way you are getting a 100% efficient heat engine. Okay? Some amount of energy is lost during its operation. Alright? So, that's all about what you call the efficiency of the heat engine, and the Carnot engine actually works on a cyclic process, and that cyclic process is shown by the indicator diagram, and that cycle is called Carnot cycle. That Carnot cycle involves four stages. Let us see. The four stages are volume, pressure, and the Carnot cycle. A, B, C, D, A. Now A to B is called isothermal expansion. Isothermal expansion. And B to C is called adiabatic expansion. But C to D is called isothermal compression. And D to A is called adiabatic compression. These are the four stages of working of a Carnot engine, and we call this as the what? Carnot cycle. And actually this area inside the Carnot cycle gives the work done in the process, because area of the cyclic loop gives the work done in the cyclic process that you might have studied. And here each stage is called stroke. So heat engine, when we discuss in higher levels, here isothermal expansion is called isothermal expansion stroke, adiabatic expansion stroke, isothermal compression stroke, and adiabatic compression stroke. So each stage of action of the what you call the Carnot engine is called each stroke of that engine. So this engine, Carnot engine, is a 4-stroke engine, we can say. So 4-stroke engine, 3-stroke, and what we call the 2-stroke engine. See, when you go for the higher levels of studies in Carnot engine or the heat engines, you will be coming across these types of different strokes of engines. And that strokes relates with what you call the efficiency of the engine and all that you study when you go for the higher levels of thermodynamics. Okay, so here we require the basic of what you saw, the Carnot engine and also the Carnot cycle and efficiency of the Carnot.